So we have been discussing about the flow induced vibration in the last lecture. So we discussed about the numerical studies and experimental investigations carried out on cylinders and application of this problem on TLPs, where we said that there has been phenomenal force reduction in the members when a cylinder which is solid is covered by a perforated layer or a perforated outer cover which has perforations all along the periphery. When this covers the inner cylinder, it is expected that under the action of waves the forces on the inner cylinder is reduced tremendously. So one can easily look at perforations or perforated covers as an effective method of reducing forces or retrofitting or rehabilitating the existing structural members which are already weak because of many reasons like material deterioration, stress concentration factors, etc. So we have shown you how experimental investigations can be conducted on a scaled model of a TLP as well as group of cylinders of different perforated outer covers, and we validated these results with that of the numerical studies form using a software by name CCM+. But we already told you yesterday that there are some difficulties of not able to trace the velocity potential variation along the depth of water when you look at application of numerical studies in this case. Primarily our interest is, though it is force reduction, but we wanted to really understand, and we have understood that whenever an outer cover which is porous or perforated, the vortex formation is disturbed. The vortex formation is disturbed in the presence of perforated covers or perforated members. So this is one of the great advantage of application what we are looking at, which is recommended by researchers in the recent studies, that this can be one of the effective method of reducing the vortex formation in a given member. In the present lecture we will talk about how this problem can be handled using analytical formulation or mathematical modeling. For example, I want to write a program on my own, a coding on my own to find out or to trace the velocity potential variation or water particle kinematics, essentially the velocity and acceleration variations along the depth on the inner cylinder because of the presence of outer cylinder. So always we are focusing on what is happening to the inner cylinder when it is encompassed by a perforated cover. In the earlier example also we saw the same thing, in the present example also we will see the same thing. Okay. So it is very simple to understand basically why this kind of disturbance happen when a solid cylinder is encountering waves. It results in flow separation and that results in vortex formation. When you have a cover which is having pores or holes, the fluid is made to flow through the holes, therefore vortex formation is disturbed. It is a very simple physical phenomenon. Okay. So this is effective in two forms: one, vortex formation is reduced, and secondary vibrations caused by the fluid flow in the vicinity of the member or the structure is reduced significantly. The second advantage is when the member cannot take the intended load because of its material deterioration, age factor, stress concentration in the joints, etc., can still strengthen the member by providing an outer cover, not on the entire length of the member but on the regions where the stress concentration is maximum. It is expected that near the splash zone you will always have the maximum forces exerted by the waves. So we can always try or attempt to put a perforated cover for a specific length which is going to be a function of the entire length of the member as a parametric study, where I can move this position of the perforation above, below, etc., and see which is going to be the optimum location of this perforated cover, which can reduce my forces on the member. Okay. Now let us look at this example again, revisit this case analytically and see, can I do a mathematical formulation of this problem and can I derive the velocity potentials for this problem mathematically. Okay, that is what we are going to look at today's study. Do we have any questions on the previous lectures where we are talking about flow through perforated cylinders? So we discussed experimental investigations, we also discussed numerical studies, we have understood that porosity or perforated cover can be one of the effective method and mean to reduce vortex formation as a designer's perspective. Okay. Now we look into the hydrodynamic perspective of this using a mathematical model. Okay. It has been seen in the literature that I am using PC for perforated covers, okay, because you need not have to write total, you can easily understand this. Presence of perforated covers generally reduces the wave impact on cylinders. There are studies reported on this. Which can be my paper and Abhishek Sharma, (2010). You can have many examples of these applications in reality. People have attempted this idea in reality. For example, rock filled porous breakwaters. There are rock filled porous breakwaters of a very large dimensions where the breakwaters remain porous, and it has been estimated and seen that there is tremendous reduction in the wave impact on these breakwaters. The second example can be construction of what we understand as open harbors. Okay. These are all very famous application examples where one can look at the presence of perforated cover or a porous structure as a mechanical mean of reducing the wave impact on members. We have another classical example of a gravity based structure which is an Aco Fisk platform. It is a gravity platform constructed in North Sea. This gravity platform has porous members which has been essentially used the moment I say members, they are structural members, okay, porous members which is effective in cover reduction, because you understand in gravity based structures, because of the mass, this cover on the seabed is a major problem. Okay. So that is essentially caused because of the impact by the waves and current on the structure, and by providing porous members this effect was reduced significantly, and people have shown that there has been a reduction in the cover. For wide crust breakwaters, designers have recommended porous members as an effective alternative. This can be seen in studies conducted by Zipping and Chuang. (1994). So, there are many references available in the literature where people have used effectively the presence of porous members or perforated cylinders or structures to reduce the wave impact on the members, but they have been essentially applied on coastal structures, though coastal structures are also part of marine structures, not on any deep water large floating systems, okay, that has not been applied. But people have used it for breakwaters, coastal protection structures, people have applied and they have seen that there has been a reduced impact. Now, let us talk about the presence of floating structures in the flow field, because this was a new attempt which is not available in the literature. Very scarce mention about this application is available in the literature. We will discuss this in detail, because about the fixed platforms like gravity based structures people have conducted studies and you can find lot of references on this, and for breakwaters people have conducted studies and you will find lot of experimental as well as analytical studies available on this. On floating structures this has been very scarce. So, let us look at that and revisit this area. The moment the floating structures are interfering with the flow field, it causes alteration in the wave field by diffraction and radiation. Of waves from the structure. Now, interestingly, this problem of equation formulation will have two solutions. One is the solution of the diffraction problem yields to the excitation forces on the structure, whereas solution of radiation potential results in motion caused by the structure which produces acceleration and velocity proportional forces. So, this problem has two kinds of solution, one is the diffraction potential solution, other is the radiation potential solution. One yields me the excitation force, other yields me the acceleration and velocity proportional forces. Now, in these two components, the acceleration proportional non-dimensional amplitude gives added mass values and velocity proportional non-dimensional amplitude gives radiation damping. Okay. Now, let us take a system this is my seabed, this is my cylinder, this is my perforated region, this is my mean sea level. I start Z from here, and of course x is in the forward direction of the wave propagation. I call this distance water depth as h, I call the diameter of the member as d suffix c, and I call this as Z1 and this as Z2 and any value here as a variable z. I divide this for mathematical modeling into 3 regions. There are 3 regions here. I say region 1, I say this is region 2, and I say this is region 3. Let us explain these regions. Region 1 refers to the outside region of the member. So, in this case r radius is greater than dc by 2, dc is the diameter of the member or the cylinder, c stands for the cylinder, and z varying between minus s and 0, is it not, minus s to 0, this is the region. I call this equation number 1. Region 2 is my perforated region, where r is less than equal to dc by 2 and z varies between minus Z2 to minus Z1. Is that okay? This is equation number 2. Region 3 is the region below the cylinder, that is this region, where in this region also r is less than dc by 2, r is the radius. Let me call this value as b. Depth of immersion of the cylinder. So z varies between minus h2 minus b, is that okay? Equation number 3. So we have divided this into 3 regions, and now I am going to derive the diffraction potential and the radiation potential in all these 3 regions independently. Okay. Now for this analysis, the flow is assumed to be incompressible and irrotational. Therefore, the velocity potential is given by calls equation number 4, where phi r theta z is the spatial component. You can see here r is the radius, z is the position along the depth of water, and theta is the displacement direction, okay, and the phase lag is the spatial component of the complex velocity potential, because it is I omega t, and Re of the argument is the real part of the velocity potential. Now the velocity potential in all the 3 regions should satisfy the Laplace equation. call this equation number 5. Okay, we will do one thing, we will use this as a different notation, we will say del square phi j. In addition, region 1 should also satisfy the boundary condition region is the outer region. This is a free surface boundary condition. Therefore, I should say this should be satisfied at z equals 0. Z is measured from the MSL. Call this equation number 6. Now, velocity potential in regions 2 and 3 should satisfy also the following condition. That is seabed boundary condition, because z is minus h. I will call this equation number 7. So, for linear water waves, phi in any region can be decomposed into 1, the incident potential, which I call as phi capital I, the radiation potential, which I call as phi r, and the diffraction potential, which I call as phi d. The radiation and diffraction potential will be valid for a count of j. I will explain this. There are 3 regions, 1, 2 and 3. Okay. Now, interestingly, when the floating structure is subjected to unidirectional waves, only surge, heave and pitch will be active. We all know that and put your thumb towards this, these 4 fingers will give me the direction of rotation this way, yeah. Now I have a cylinder acted upon some force, velocity variation. So the force, this becomes the x direction, so I will have such, and we all know in a floating system the set down or the heave and the surge motion are strongly coupled, set down and offset are coupled, therefore I will have heave, and the differential forces at any point will cause a moment, and that moment will be about normal to this axis, nothing but pitch, okay. So we will have 2 translational and 1 rotational, degree of freedom active when the wave is unidirectional, okay. So only 3 modes will be active, surge, heave and pitch, though it has got 6 degrees of freedom, but we will active only 3, okay. That is what I am writing here, only surge, heave and pitch will be active. Therefore, phi can be expressed as incidental plus diffraction sum of so, you can see here the summation is done only for 3 modes. What is the equation number here? Where del m is the displacement in mth mode. Phi d and phi r are diffraction and radiation potentials in mth mode and jth region. Okay, J stands for the region. How many regions do we have in this problem? 3. Region 1 is the outer periphery, region 2 is the porous periphery or the porous region, and region 3 is the region below region 2. We have defined the boundary conditions for these regions, okay, in equation 2, 3 and 4. Now the incident wave velocity potential is given by my I, which is IGH by 2 omega equation 9, where let me check this equation first. This is I, okay, this is I am Jm. Del 0 is equal to 1 and del m is equal to 2 for m equal to 1, okay, greater than 1. For any value of m greater than 1, you can say this value is 2. When it is 0, then it is taken as unity in this expression. Jm is a Bessel function of first kind of order m. H is the wave height, of course, and K naught is the incident wave number. Now, in our example, since the perforated region is homogeneous, let us say, and isotropic, the flow should obey Darcy's law. In that case, fluid velocity within the region is proportional to the pressure difference between the walls of the perforated region. Hence, the continuity equation on the normal surface means non perforated and the perforated region will be given by let me call this equation number 10, is it? So, this is for normal surface and this equation is for perforated surface. Where V is the structural velocity vector and Vp of theta z. Is the spatial component of the normal velocity the normal velocity is Vp of theta z of t which is valid applicable to the perforated region only. Such that there is a condition which should be satisfied. Vp of theta z of t is real component of V theta of z E minus I omega t. Call this equation number 11. Now, the fluid flow in the perforated region should be a laminar flow and obeys Darcy's law. In that case, Bp theta of z is given by nu by mu rho I omega phi 1 of dc by 2 theta z minus phi 2 of dc by 2 theta z. Let me check this equation. I call this equation number 12, where nu is a material constant which has dimension of length in case of units. Mu is the coefficient of dynamic viscosity Let us now define a parameter called porosity effect parameter, which is defined by S, which is given by rho omega r by mu k naught. This is the dimensionless parameter which depends on density of seawater, diameter of the pores, and properties of incident waves. This parameter was first suggested and dependency of these factors were established by Hugh et al. In 2002. Then the porosity effect parameter S, for S becomes 0, indicates impermeable wall, okay, and S equals infinity indicates completely permeable wall, that is wall does not exist. In the present study we have assumed S is equal to unity, which indicates partially permeable wall at a specific frequency of 0.3 radians per second. Now, one can compare this porosity effect parameter with a well known established relationship Reynolds number by using dispersion relation. Now, by using dispersion relation, the porosity effect parameter S can be defined as call this as equation number. What is the equation number? 30. Where Re, this Re is equal to rho nu Gd by mu, which is comparable to the Reynolds number. Because Reynolds number is rho Vd by mu, where rho becomes a material constant, which is analogous to D of the pipe and root Gd is analogous to average velocity of flow in the pipe. So, what does it mean is, once we can establish the porosity effect parameter as similar to that of Reynolds number, which indicates that the fluid flow is similar to that of a pipe. So, I can say now the flow through porous region is similar to that of flow through a pipe. So, we stop here, we continue this lecture in the next one, where we will continue to derive the other velocity potential components, and then we will apply this on a floating platform and see how I can compute the influence of these parameters on the force reduction in a floating system which is having porous members. Thank you.